This is actually the heart of the melon here. How to do CAN, what the tools look like, and how to make that work. I can parachute out of a plane. I know how to do that. And I could probably make a parachute. I have diagrams and understand parachutes. And I have material I could probably get to make a parachute, the nylon and so forth, and the machinery to make a parachute. Our right turn into CAN reverse engineering, I kind of feel like I've jumped out of a plane with a bunch of parachute material. All we have to do is sew it up, put it on, and pull the ring before we hit the ground, and then it'll all work pretty good. Along the way, I encountered Collin. We started with the Makina board from Recharge Car, an Arduino Mega that had a CAN port in it, and kind of a really bad library to work it. And Collin reworked that library to be more effective for that. He was the central architect to bring to fruition my dream of a generalized electric vehicle control unit to control the DMOC 645 inverter. When we went to the Coda inverter, we had a pernicious and vicious little security byte made from a polynomial CRC thing with an unknown string that I simply could not figure out how we were going to do this other than just collect a lot of different torques and make a huge table of these bytes and look it up. In a matter of days, actually, not even a week, he worked out a 5-line bit of C++ that gives me the correct byte. And this has been a recurring theme where I come up with a problem that I just don't know how we're going to get past, and Collin spends a good part of an afternoon on it and emails it to me. And this went on for several years, and I finally asked him to join the EBTV staff at a distance. And so he kind of works half-time for the family business, half-time for EBTV. And most of it is all the stuff I can't do, Collin can. And that's a neat guy to have around. The parachute analogy is about we have to capture CAN data, we have to reverse engineer it, and we need the tools to do that, and didn't have them. We kind of had the JevQ, which can do some stuff with CAN, but we really needed tools to capture CAN data and perform analysis on it that takes months with an Excel spreadsheet and sometimes 45 minutes with his SavvyCAN software, which is all the good parts are all the parts I would want out of Vector's Canalizer $12,000 software suite. And he's even more brilliantly gone to an entirely new development system called Qt, where he can simultaneously support Windows, Macintosh, and Linux versions. I absolutely detest Windows in its entire existence. And he views Apple as the ultimate evil empire. And in fact, it's amazing, I don't think we have anything really in common. Except that we do kind of like to doodle with code and technology and electric cars. He's recently near completion on a conversion of a 1959 Mercedes-Benz SL with a Coda drivetrain that goes 130 miles an hour. Direct drive, no transmission. And so from the theoretical, he's really actually kind of part of the Arduino development team now. Sort of advising them on what should go into the core. And so from the theoretical to where the rubber meets the road, he's got a finger in all of it, and has been a joy to work with. And we're very pleased to have him with us. To do CAN, you need tools, and we've had to develop them while we're trying to reverse engineer the CAN data for automobiles. And that's where the parachute analogy comes from. All I have to do is jump out of the plane, sew up the parachute, put it on, and pull the ring before we hit the ground, and it'll all work out great. Don't try that without Collin along. And along the way, he's developed a very simple program that will run on our hardware, a CAN Dewey, a couple of things we have for CAN using an Arduino Dewey as kind of the hardware end of it that feeds the laptop where you capture the data and can graph it and compare it and perform various analysis on it, that he calls SavvyCAN. The part that goes on the hardware is called the Generalized Vehicle Reverse Engineering Tool, GVRET. And the real reverse engineering tool is the SavvyCAN, actually. But this is the header, or your capacitor, or your micro USB, or whatever you would normally use as hardware to connect to a CAN network. We've got a little better hardware that can do things a little faster than most of that that's out there, with his software a little better, and that feeds a more powerful laptop with a more powerful analysis tool. And so this is probably the session, if we were going to have an open house this year, that you actually will probably need for the future. And I think some of you are going to say, I don't really need that. Work with me here, things change, and 6 months from now you may feel differently. Would you all please give a warm welcome to Collin Kidder of Sparta, Michigan.
Hold on, there's something. Hello.
Hello.
I'd like to go over a variety of reverse engineering things. I'm going to start with the hardware. Jack kind of went over that a little bit. The first thing we kind of start with the Arduino Dewey. He kind of covered. That's just the base board. It has CAN bus. You can actually see, well, you might not be able to see very well, but it's labeled CAN RX and TX right there. They have pins, but as he mentioned, there's no transceiver on that board, so it's not really possible to directly use that. So we've made this board. It's a shield that plugs over top of the other one, and he kind of showed how there's transceivers. There's the two transceivers right here for the CAN bus. There's a single wire transceiver here, the EEPROM up there, and switchable termination. So that pretty much adds everything you could ever really hope for in a hardware tool for capturing. We have two CAN buses, 1 and 2, the NTC temperature input, single wire CAN. So everything is on that one board. I've actually got one here. That's what it looks like all put together. It's kind of stacked together and uses micro USB to hook up. So that's been our ultimate in capture boards. GVRET runs on that board and allows us to do capturing. Actually, as well, one of the things a lot of the cheaper boards that you can buy do not have are isolated CAN bus transceivers, but this does. The advantage in isolated transceivers is that noisiness on the CAN bus doesn't backfeed through into your laptop and blow anything up. So that's kind of handy. Also, I failed to mention it does have a micro SD card on that CAN Dewey 2 board that we made. Jack didn't think that was very useful, but I actually use the micro SD card a lot. GVRET has the capability to automatically log when you give it power, and I'll show that in a little while. So it can log as soon as it gets power. You do not need a laptop connection. It will save in the same file formats that SavvyCAN can save in. So you can use that tool. In the 190SL project, what I would do is take this and shove it up under the dash connected. So the whole while we're driving, it's logging data on both CAN buses that I have in the car. So I'm never without a log. Anything that happens in the car, if screw up happens, I can go right back, pop that micro SD card out, and I have full logging data. So I actually think that's a very handy feature and not normally found on CAN bus capture tools. You can get a $1,000 Kvaser tool that has micro SD, I think, but I mean, nothing in that price range really has micro SD capability like that. This is the EBTV Dewey. Is pretty much the two boards we have here smashed together, but just with one CAN bus. But for the most part, that's probably, if you're just going to do captures on the CAN bus, this is a pretty handy tool if you just want a single board. Another really nice thing with this one is that we use it's called USB-B, normally found on printers and modems and such. It's a lot larger and sturdier. These micro USB ports, they snap off the boards really easily. And you can pretty much ask me how I know that one. I have stacks and stacks of Deweys with no USB ports. So this has all the stuff you really need. It's less full-featured than the CAN Dewey 2, but it's cheaper. It has everything you need, and the USB-B port is practically impossible to snap off. So that's kind of useful. Jack also has this Tesla package. It's, I believe, pretty much this two-stack of boards, but inside of a housing with a nice USB-B plug and the Tesla diagnostics connector. That's what he's been using to get our capture logs for the Model S work that we're doing. This, the mating connector for that is underneath the center console on a Tesla. And it's not protected by anything, and Tesla really can't turn it off. So that's really quite handy. Some of the hacking attempts that people have done in the past, they've tried to use Ethernet and some other diagnostics ports that Tesla was able to turn off. So the handy thing here is the diagnostics port under the center console. This is a direct connection to the CAN buses on the car. There is nothing to stop you, no real practical way that Tesla can disable that because it's hardwired right into the car. GVRET is the firmware that runs on these. It is a sniffing tool, so not only is it the glue, but you can sniff it. It supports everything. It does also support, you can run GVRET on a JevQ if that's all you have. These little tools are kind of nicer in some aspects for being able to put into the car and drag around portably, but if you already have a JevQ, you can actually use it for the capture and reverse engineering as well. The GVRET has text mode reception. I'll show that. I specifically designed GVRET. He was talking about how SD cards are slow. That's just because the native or the normal libraries for Arduino aren't very fast, but GVRET uses a specially modified one. I think the right speed is something like 4 to 8 megabytes a second on the library that I'm using, and you can't capture CAN bus traffic that fast. The maximum CAN bus speed is 1 megabit per second. So really there's no problem. You can write to SD card as fast as the CAN bus will go. It is also open source. Really pretty much everything is. All of our board definitions are open source. GVRET's open source. SavvyCAN is open source. And it communicates with SavvyCAN over binary. There is text mode, there's binary mode. SavvyCAN just automatically sets it to binary mode for a little extra performance. SavvyCAN I wrote, as he mentioned, in Qt. It's actually pronounced cute, but I say Qt because it looks like Qt. The reason we did that is for cross-platform desktop development. I use a lot of Windows and Linux. This machine runs both. Jack uses OS X, which I refuse to use. So for development, we really wanted something that would be cross-platform. I had a previous tool that was written in C# that really was not cross-platform. So it's been switched entirely to C++ with Qt. I like C++ because of the speed and power it gives you. A lot of people aren't always so partial to seeing C++ code, but really it's pretty clean. And it doesn't require anything really other than the Qt libraries. So you could see if you try to compile GVRET, the list of libraries you need for the Arduino sketch is very long. It's fairly hard to compile, but this SavvyCAN is actually fairly easy to compile. Custom designed really for everything that I wanted to do for reverse engineering, with inspecting frames, replay playback, replay data, DBC, which I'll cover in a moment. Here's what the main window looks like in SavvyCAN. I'll be doing a complete walkthrough of SavvyCAN later, but you can kind of see it as it came through. This is the timestamp in seconds. This ID extended of 0 means it's they were standard frames. If it was a 1, you'd see 1s there. It supports dual bus capture, so the bus can be either 0 or 1. Then how many bytes were sent on this frame and the frame data. But I'll go through SavvyCAN much more thoroughly later. It's kind of useful to see and know the differences here. In SavvyCAN, a lot of things we do use hexadecimal. Like Jack showed before, 0x tends to show you that it's a hexadecimal number. I have octal in here, but unless you programmed computers in the 70s, you probably don't care. And the decimal equivalents, these are all equivalents, binary. Jack covered before that in hexadecimal, every digit in hexadecimal is 4 binary digits. So that's why we like to use that. It looks a little funny sometimes. You see 0x80, you don't know what that means, but it's a lot cleaner than 128 here has values in all 3 places, but you can see here it's only 1 bit. So this gives you a little cleaner representation of the bits. When you get used to it, it's a little easier to interpret data. Now, when data comes in the CAN bus, you can have up to 8 bytes. Like Jack showed before, they do start labeling as 0, so 0, 1, 2, 3, 4, 5, 6, 7. And the bits within each byte are labeled 0 through 7 as well. So this is how bits are laid out and how they're numbered. Ordinarily, you wouldn't need to know this, but when you get into DBC files and trying to interpret data on the bus, you do have to start figuring out the numbering system. So it numbers 0 to 7, starts back over 8 to 15. The bits are numbered sequentially. Kind of, it looks backwards, you might say, from how people normally count, because you're counting right to left. But that's how the bits are stored. And that's kind of important when you talk about DBC files. The really weird part when you cover DBC files, though, is little endian versus big endian. I should probably go back and mention, when you have more than 2 characters here, a byte can store 2. So when you store this, if you're going to store a value of, say, 25,797 that turns into this number, there's 2 ways to store that. You can store it as C564 or 64 C5. This is in big endian mode, where the largest value is first and the littlest value is second. For some reason, various computers practically randomly picked which way they store multi-byte data like that. And in a DBC file, complicated as it seems, if you start at bit 12, let's say up here, and you're going to store an 8-bit number, which unfortunately they sometimes do, this will go 12, 13, 14, 15, start back over here, 16, 17, 18, 19. That's where the data will be stored in little endian mode in DBC. You hope that they won't do that, because normally if you store an 8-bit value, you'll say start here and end here, and it doesn't really matter which direction you start counting, it's all in 1 byte. But they do store them, and I'll kind of show that. Sometimes they store values across different bytes, and then this difference comes in little endian versus big endian. The weird one, and unfortunately Tesla does do it, storing in big endian, you will sometimes get, you can see here I showed, if you started a 8-bit value on 12 in big endian, it would literally go 12, 13, 14, 15, and then start over 23, 22, 21. You know, it goes from the opposite direction. Believe me, it's confusing. But that's kind of necessary to understand DBC files. The general basis of a DBC file is to just define a signal that can be seen on the bus. If you encode, say, speed or RPM, throttle or faults, you stick those values somewhere in this big grid. Let's say you might have these 3 bytes mean the gear. So the DBC file will tell you bits 29, 30, and 31 mean gear. The nice thing there is you never have to worry about that again once that's defined in the DBC file. The DBC file starts with nodes. Nodes are, like Jack showed, if you have devices on the CAN bus, each device, according to a DBC file, is called a node. Each node sends and receives messages that have a given ID. So each ID, let's say a message has an ID of 400, that forms a message. And inside each message are signals that encode things such as the speed and RPMs.
Could I generalize this just real quick, Collin?
Yeah.
That DBC file is a dictionary that you can keep, and you can make one. But as you reverse engineer stuff, you can store this in this DBC file if you follow this kind of convoluted format. And it acts as a dictionary, and his software will read it and then interpret the values based on what's in there. It's a way of saving what you know. If you have a DBC file, we have one.
Yeah, we do have DBC files for some of the things, and it is basically a dictionary.
It's a dictionary. It's where you look up what's all the data bytes, what do they do? And it's a way of keeping track of it. So it's a dictionary file for CAN.
This would be a little more clear. I'll show you in SavvyCAN how the DBC functionality works. That'll probably clear up the way it...
Is that dictionary by language based on vehicle language or component language? You follow what I'm saying?
No.
You have a DBC file saying this number means this throttle position.
Oh, yeah.
Is that for that vehicle only?
It's for that vehicle, yes.
Message
Well, for that hardware.
It's for that message and that byte only.
Could you pull up the transit
Which
connector?
varies from vehicle
Could you
to
pull up the
Oh,
transit
absolutely.
connect one and show
and
them real
component
quick?
to component?
Yeah, I will show that, yeah.
But
I have a couple DBC, I have the DBC file that we started making for the Tesla too, so I can kind of show how that
if
works.
you reverse engineered every message in it and kept your DBC file up, you would wind up with a dictionary to the car.
Yeah. I'll show too why DBC files are handy, because all of this gets complicated and you only want to do it one time. Once you can encode that in the DBC file, you don't have to worry about that complication ever again. The DBC file is the dictionary and the translator for you. It's very handy. But I'll show you that in a moment. So how do we kind of put all this together? The first thing we have to do is start figuring out how to get on the CAN bus. I mentioned on the Tesla Model S, that's under the center console. There's a plug that Jack's special box can plug into. Then we have to try to capture some traffic. At first, we may not know the speed or even the pins it's on. Luckily, on the Tesla, we had a pinout chart for the diagnostic connectors, so we knew how to wire that. And we had some reference for the speed. As Jack said, normally in a car, the speed's going to be 250 kilohertz or 500 kilohertz. So you can pretty much guess, but if you guess and try capturing some traffic, you'll see if you get any. The next thing to do is try to go for a drive, just capture some general traffic. It's also nice to capture and log the separate files, various things that you want to figure out. Activate the door locks and save the file, shift the car into, say, drive to park and shift and save the file. Do various things and save them to different files so that you can get some reference of what changed in that file. But the most important thing is we do need to get some traffic where you didn't do anything, just as a baseline of comparison against these things. If you compare traffic when you didn't shift the car to traffic when you did shift the car, what we'd be looking for is what changed. And SavvyCAN helps you to do that. I just covered one approach is to compare the do nothing log against the other logs. You're looking for new IDs, new values that didn't show up before. In SavvyCAN, we can also graph things, and a lot of what we found, when we find RPM and torque values, a lot of times what we're doing is graphing data and seeing the value kind of smoothly move, and that's giving you an idea that maybe it's something throttle related. Then once we get that data, we're trying to guess. Sometimes we'll see throttle data, or we're fairly sure it's RPM, but it might be scaled funny, say 10 to 1 and not 1 to 1. So sometimes we have to kind of look at the scaling, but you can use some educated guesses. If you know that the RPM is capped at 16,000 and you asked somebody like Jack to floor it across the bridge, then what you can do is look for data and see when it hits 16,000. If it hits 16,000, you know that you found the RPMs and they're scaled 1 to 1, which I think on the Tesla it was.
If they let you email files from jail.
Yeah. Yeah. So there's various things that could go wrong or could complicate things. One of the things I mentioned, a lot of times you want data that's found in 8-bit increments so that when you look at the bytes, it's all packed in 1 byte or 2 bytes or 4 bytes neatly. Not always the case. In Tesla, sometimes they use 13-bit signed values, which is kind of complicated when you look at the bit patterns. So sometimes you'll see what the case is. Sometimes on the Model S data, a 16-bit signed integer would have been normal. What they did is took the top 3 bits in a 16-bit integer and put a counter in there. So the top 3 bits go 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. And so when you look at that data, you see huge jumps as the counter is counting, and it's counting in the highest position. So it looks terrible. I mean, the data looks terrible. You have to try to get rid of that. That sometimes throws you off. Sometimes this pretty much goes with point 1. Sometimes data is stored only in part of a byte. The rest of that byte has another purpose. It could be nothing. It could be a validation. It could be counters. Quite often, and this is one of the things I did my previous year's presentation was on the UQM security byte. A lot of times Tesla has this as well. What they will do is the end byte. When you have an 8-byte frame, the end byte will be a security byte that is encoded based on the first 7. So sometimes you have to crack that, and that's kind of complicated to do, but my previous year we kind of covered that. And sometimes, and I really hate Tesla for this, sometimes data will only briefly appear or be in hard to catch places. We had found on the Tesla that when you shift gears, you have a blip in the data and it disappears. It does not permanently set the gear on the Tesla. You get a setting for 2 or 3 frames.
10 or 12 frames.
And they're gone.
2 or 3 frames.
So you have to be quick to catch it. And it's very easy when you're looking through all that data to miss a little blip that appears for a couple of milliseconds and disappears. So that kind of complicates things a bit too. I'm going to go through a guided tour of SavvyCAN now. Hopefully make things a little more clear.
Is that the blood moon?
There. Have to see how easy this is to use my mouse cursor here. This is the main window in SavvyCAN. You can see here I've selected COM3 and I'm connected to it, but I'll disconnect. If you have a GVRET board and you connect to it, you'll see down here it shows that you're connected and which version of GVRET you connected to. So I have 325 as the version for my connected GVRET. When you connect to it, it'll automatically fill in the buses here for the speeds. So I'm set to 500 kilohertz for speeds. You can see total frames captured and frames per second captured. You can suspend capturing if you don't really want to do it anymore. The file program here has a variety of preferences for what you'd like to do. It can save and restore window positions. So when I opened this, it achieved the same position and window size as when I left it. That's kind of handy. You can resize the windows for your computer so that when they come up, they're the size that you're looking for. There's a setting to display values in hexadecimal. If you deselect that, virtually everything in the application goes to decimal. But as I covered before, it's kind of easier to use hexadecimal when doing these things. You can either turn off the validation of the GVRET connection or leave it on. Usually I would leave it on. Displaying time in seconds, if you turn that off, it displays it in microseconds, which I find a little bit more difficult. A lot of these are somewhat advanced settings. Use filtered frames and sub-windows. When I cover filtering, you'll see that you can filter out the main list and look at only some of the frames. If you click this, then all the sub-windows will only use the filtered list and not the master list. There's capability to put the second CAN bus in single wire mode, which is the only CAN bus that supports single wire mode. So if you need that, you can select that there. Most of the rest of these are just preferences if you prefer things. You can make the main form here auto scroll when you get data. If you don't select that, then wherever you're at, it'll just keep filling below you. I feel that normally for me, auto scroll would just be annoying, but you can turn that on or off if you like. Then in flow view and some of these other things, these are just settings that will automatically check boxes on these other windows or automatically bring things in on the other windows. But I'll cover that more when we see those other windows.
Sometimes this can be hard to juggle driving. The clear frames button is your friend. I get it capturing and I'm driving, and if I clear frames, that wipes out all the frames from memory, and that's your start. So I've already, before I ever left the garage, I've got it capturing. But when I get out on the road and want to say, okay, now I'm going to accelerate or I'm going to put it in reverse or whatever we're doing, I just hit clear frames, and that wipes out everything and it starts collecting from there. That's my base point.
So if you're done with something in 10 clear frames, it's gone.
Then when you finish your test, you just save the file, and that's what you have.
The load file screen and save file, it can load and save in the same formats. They're exactly the same. These are all the formats. Busmaster is kind of a competitor open source reverse, well, not really a reverse engineering tool. It's essentially an open source canalizer. It's kind of hard to use. Some people have microchip capture cards, and we can load and save in that. But the default formats here are CRTD and GVRET format. I have the defaults for most things set to CRTD. What that is I don't know if anyone has heard of Open Vehicle Monitoring System, OVMS. It's a board made by a man named Mark Webb Johnson. It's an open system to monitor Teslas and some other vehicles. He made this CRTD format in relation to that, and we decided long ago that we were going to standardize on that so that all of the OVMS people and all the SavvyCAN people would have a format that they could both load. So that's the reason that that comes up as a standard. As I covered before, when you see in the frames, you get a timestamp ID, whether it's extended or standard frames. Extended would be the ones that have 29-bit addresses. Standard just have 11-bit. Which bus it's on, the length, and the data bit, or data bytes. Now, in this program, anytime you see a hex value, it really will be preceded by 0x. So that tells you that this is all hexadecimal. The normalized frame timing button here, if I click it, you'll see that the very first frame went to timestamp 0. You can use that to take all of your captures and normalize them a bit so that the captures all start at 0 time. It's not really important, but sometimes it's nice to be able to get the captures normalized all to the same point. So over here is filtering. This is every ID that was on the bus. And this was a capture that Jack took of using cruise control on the Tesla. So this is every ID on a Tesla drivetrain bus. But let's say that I'm not interested in all those things. I want to know about just ID 106. So if I say none here and select just 106, you can see that now I only have the 106 messages. That can kind of declutter a little bit. Now I can look here. Maybe I'm interested in how these bytes are moving. And if you look here, you can see this is 31, 32, 33. It seems kind of like those values are incrementing slowly, now de-incrementing here. It seems kind of even. And then you can see that the top thing up there, you're going 0, 2, 4, 6, 8, A, C, E, and it's cycling. So you can tell this looks like a counter. So sometimes it's nice to filter to only one message and look and see what's actually changing. As that message continues to be sent on the bus, you want to know what's changing, how does the data change over time. So you can kind of filter that way. I can go back here. Maybe there's just some I don't really care about. You can just pick out the ones you don't care about. Up here, there's functionality. You can save the filtered list. Let's say that I want to use a different program to do some analysis, or that I want to export to Excel, say, just the 106 messages. You can select just 106, come up here, save filtered log file, and you'll get just the 106 messages saved to your log. Also, one of the things that we do, you can playback here, and it popped up on my other window. Playback window. It's a little complicated, but what you can do here, you can actually play back different files. Let's say what we did when we were first trying to get the inverter to work is we would take this drive around circle file that Jack made from a real Model S, the Tesla Model S. He captured this driving around the block here at the shop, and we want to play that back on the bus to try to get, say, the bench-mounted inverter to work. So you can load up that file, say loop once. I'm going to loop the sequence. And up here, these green arrows move by one frame at a time. So if I wanted to just slowly play through these frames, I could. Otherwise, here, we're playing back. The playback speed is in milliseconds here. I'm playing back 1 frame per 5 milliseconds. Burst rate is how many frames to send every tick of the playback. So if we really need to start sending fast, you can send the burst rate up, and you can see it really starts to speed up.
Let me interject here. this is kind of important on some systems. There's only one setting on the left and one setting on the right. They both have to be set right, or the Tesla drivetrain doesn't do anything. And that's how we learned what the timing was. It has to receive these messages at a fairly narrow rate, or it simply doesn't work.
The reason, that is the reason for this burst rate. The Tesla wants 1800 frames per second, and Playback can only really go to about 1 millisecond. So that would ordinarily get you about 900 frames per second. But with burst rate, we were able to bump that up and get the 1800 frames per second. We could play this file back fast enough to make the inverter respond.
But you still have to extrapolate that. There's 193 messages, and so at some point we had to do a translation that these messages have to go every 100 milliseconds, these have to go every 10 milliseconds, these have to go, but this is how we got there. We had a boat anchor until we got the right combination. In fact,
you can see
Collin
here
had to
ID filtering.
Code burst for me.
What we did is we would play this back and start deticking these IDs. In Playback, you can detick the ID here on filtering and it will not send those IDs. What we did to figure out what was the minimum baseline to make the inverter work is start deticking these until the inverter gave up. And if, let's say, deticking 116 makes the inverter stop, then you retick that, keep going. And Jack literally had to go through all of these
193 and find 7.
To find just the 7 messages, but that's how we did it. That's a way to reverse engineer what messages were required. You can play back on the bus, filtering out the IDs you don't need to come up with just the ones that you do need.
Collin, is there any plan to have the Playback read the timestamp from the log file?
I've thought of that. It doesn't do it yet, but there is that possibility that it could be done. Just I know what you mean, to keep the timing even the way it was when you captured it.
Right, automatically set the time in the burst.
Yeah.
Jack justified the grouse that he's ordered some switches that will send the CAN bus message, right? And so if we have those and install them, can we use those as markers to inject that CAN bus signal that'll be ignored by the car, but it goes in the raw log file when we start looking for an event?
That is a good idea. I think we might have talked about that, having something like that that you could trigger. It's a very good idea to be able to do that, because otherwise you could see the capture that I had was something like 196,000 messages. That's a lot of data to process by hand.
And even finding where you're at in it, one of the things we did do was took our CHAdeMO device that measures current and voltage and temperature and had it inject current and voltage and temperature into the stream. And so then I could look for voltage, and I knew what voltage the pack really was at that point. And as you accelerate, of course, the voltage changes, and so I could see the change, and I'm looking for a bite from the inverter, not from us, not from the car, that changes. So yeah, you can find various ways of inject. Basically, when you get to a component and you're trying to control it, in other words, after you get to the 7 messages, what's in them, you have to set up some sort of sensor, a way to read temperature to compare to the data, a way to read voltage to compare to the data, a way to read current in real time and compare to the data. And if you can actually inject it in the file at the perfect time, that makes it tons easier.
Yeah,
So
that is a good
switch
point.
idea is actually pretty good.
And we did do that. He had the JLD 505, I think, on the bus at the same time, and that is a very good way to find data points that if you can measure them externally and try to look for them in the data that you have there, it's easier to correlate. You know, if the JLD 505 says that you have 360 volts, then you're looking for 360 in the data.
Do we also have the capability of color coding those switch lines when they inject? Because if you're going through thousands of lines, well, you can pick up a color quick.
You know what the ID is.
Well, yeah, but comparing a number to a color.
Color by ID number.
We probably could color it by ID.
This is a cool feature.
That'd be a neat
It
feature.
would be kind of a neat feature. Luckily, Byron's recording this, so I'll probably forget otherwise. I'm going to quickly show this in terms of if you are kind of playing around. Like Jack said, we knew the 7 messages that we wanted. This is probably the most advanced feature in all the program. It's a custom frame sender that basically uses scripting. But what we can kind of do is, let's say you want to test out ID 006. No, not 67. What this one lets you do is we can kind of send data and have triggers and modifiers. What we could do is, let's say you know that the car needs to send this message every so often. You could put your trigger at 10 milliseconds, and it will send this message every 10 milliseconds. And you know that the car is looking for a counter in bytes, the last byte, which is 7, because we start at 0. You can actually do this in this program, or in this section.
What did you just do?
This is a script here. What I've done is I'm saying that we're going to send a message 106. It's going to have 8 bytes of data. The bytes are 1, 2, 3, 4, 5, 6, 67, and 8. We're going to send it every 10 milliseconds. And the modifiers here means we're going to take this value 8. We're going to add 1 to it and send it. And the next time, 10 milliseconds later, we're going to add 1 to that again. It'll turn to 10 and send it. So you can kind of build counters that way.
I didn't know how to do that.
Like I said, this is probably the most advanced section of the program because, you know, it's powerful but kind of complicated.
You could also screen
And
for
see,
a response
I
from the
just
device.
started it. You can see what it did. It is constantly incrementing this byte now because I said to always turn that byte 1 higher every time you send.
It gets to FF and
So is that how you check your speedometer function based on injected code?
Yeah, you could, if you were looking for the speedometer, let's say, and you wanted to test the speedometer, and let's say you knew, I'll turn this off a second. You knew that the speedometer was using these 2 bytes to pick up speed. And you could come in here and say, oops, lock that into position, which I could have done over there in data, but that's a little more complicated of a line.
He's invented his own script language.
There you go.
As the guy that's got to document all this, I'm here.
But yeah, so you can kind of use scripting there to script various sending sequences to just test things out. There actually is, I'm writing documentation for this, and that was one of the first screens that actually has documentation. So there is a whole big HTML document of the scripting system for triggers and modifiers because it's kind of a large topic.
I'll be re-releasing that in English shortly.
Yeah, it might need some translation. So that was those. I'll cover the reverse engineering tools here. This is kind of actually the meat of the
Yeah.
thing.
Questions?
Questions and feature suggestions.
All right.
So how about a binary view mode? So you can just view the whole 64 bits.
There is.
Oh, you've got that already?
I haven't,
Okay.
I haven't
Flow
gotten
view,
to that
that's
yet.
my power tool,
Yeah, flow view is something he likes.
because it has colors.
So,
And what would be cool would be to, if you've got the timestamps, it would be nice if you could display the data positioned by the timing. So have a visual representation of when the packets are arriving. So if, like a time scale, instead of just being packet, like have it in milliseconds or something, and the
Stay with
packets
us.
clustered
Then
together.
there are some other screens.
Are graph view and flow view.
Oh, those are
and
coming?
He's
Yeah.
gonna show it.
it's kind of a large program, so
Yeah.
we're kind of
Got
still
it.
getting there.
It's amazing what he's put in this program.
And the packet
When you see
sender,
graph view, you're going to shit.
can you trigger packet sending on
Actually, yes.
arrival of other packets?
Yeah, that custom sender I just showed,
Yeah.
one of the triggers is to trigger on reception of a incoming packet.
And then
And in fact, in the modifiers, you can actually grab data from other
the other
packets that
packet?
came
Oh,
in
good.
and fill it into this frame.
You already thought of that.
So, yeah, that's a very complicated screen. I didn't think we wanted to, go
I don't
over
know
an
how to
hour's
use it.
worth of.
I can send them.
No, I'm just
one
happy
frame.
knowing it's there.
Yeah, that would be probably an hour to cover that whole screen, so we kind of glossed over that, but yeah, you can do all that. File comparator, I kind of used for things, let's say my file of interest is this cruise 1, the first time Jack turned cruise control on in the car. I'm going to load up as the reference no cruise. And this is what I was saying before, how you might sometimes want to compare when you didn't do something to when you did do something. In this window, you can compare a reference, and you can load as many files as you want for reference. I mean, I could load up park to reverse on the reference too. And what you'll see here is if an ID was only found in your file of interest here, it'll be listed. If an ID was only found in your reference frames, it'll be listed. Otherwise, you can kind of see here, these are all the IDs that were the same between the two. But in here, I can look and say, in 106, the reference frames has some bits set, and here's the actual bit number. When I showed that 64-bit grid, these are the numbers from the grid, 46, 47, 55. But this is the byte and the bit within that byte. So byte 5, bit 6, byte 5, bit 7 were only ever set in the reference frame. They weren't set in the cruise frame. Does that mean something? Probably not. But sometimes you find data. For instance, on Byron's Transit Connect, we were looking for the heater message. And the heater is 4 zones of heat plus the pump to turn the heating pump on. So we knew we were looking for about 5 bits, we were hoping, that might be toggled when those zones turn on and when the pump turns on. So we actually used this to look, and I did kind of get pretty close to finding it until we eventually figured out that we have a DBC file that had the data anyway, so we get.
Oh yeah, that's right, we got a DBC for that.
So we just gave up and used the DBC file. But what we'd be looking for here with file of interest, you probably want to look for bits that are only set in cruise control. So you would kind of click through here and look for things that were only set in the cruise control, just to see. You can look at this too, and you'll find values that were only found in one or the other, and try to see if any of that looks like maybe it's an area of research. This is kind of a tool. What you're doing is looking for areas of opportunity. It's probably not going to really open up the doors of wisdom, but it gives you an area to look for. You can kind of see where, if you see here, the values, there were never any different values, you know not to look at those areas. So it's kind of helps you to know what not to look at. Kind of similar to that frame data analysis. Looks at just the loaded data, which was cruise 3. You can see that down here. If I want to see, say, ID 116, It'll tell me how many frames of ID 116 there were, what data length that has. And the average interframe interval for this is about 10,000 microseconds. So basically, this is sent every 10 milliseconds. Now we can drill in here and find out what values these data bytes had across the entire range of capture. And when you're looking for data, a lot of times what you're looking for is something that actually changes. So we can see this was always 40. This was always 0. We don't care about those. They probably don't mean anything. Data byte 2 here, though, went all the way from 0 up to FF, which is 255. So it has the entire range. If you click the histogram here, you'll see which values were found and how often. The values are in both decimal and hex. So I can see a value of 7A was seen in this byte 129 times. Value 51 was seen only 18 times. So we can kind of use that to get an idea of what these bytes are doing.
Let me point out something here. Most of the frames go up in the Tesla at 100 milliseconds. Some of them are only sent every second. 10 milliseconds is a pretty fast rate. Somebody thinks that's important.
Now you can judge the importance of a frame. Two ways you can judge the importance of a frame. As Jack covered, lower IDs have more precedence on the bus. So they will almost always, when you see inverter messages, and the Tesla is no exception, the inverter messages on a Tesla are 200 and 100 messages. They're fairly low in the ID, so that you know those messages are very likely to get sent. It's kind of off the list because it's in E, but there's an ID of just E that's on the bus here. That encodes steering position on the Tesla, and I think it's involved in the ABS and traction control. So it has an ID of E because the very most important thing is to not crash into a tree. So that ID is sent.
If you do, we'll make you an offer on your
So that ID is sent very rapidly and on the very lowest ID.
So that's a 1110.
So that they know. So that that data gets through no matter what.
100 millisecond frames, and you come across one that's being sent every 10 milliseconds, somebody did that for a reason.
You don't want any delay.
Can you sort that list by the interframe interval?
No, you can't at the moment, though that might be a good idea. Also up here, you can see Jack mentioned how many messages are on the Tesla bus. It's 187 unique IDs. In
that capture.
In this capture, yeah.
Bit field histogram.
Bit field histogram is the entire thing. If you want to know how many bits were set across here. Sometimes, if let's say we're looking for the gear selector, you might look to see when a certain bit gets set for only a certain amount of time. 232 is kind of a good one. When you see this, you can kind of see this has the same number of bits set. It's 2209. If you look up here, the number of frames is 2209. So if you see in the bit field histogram that it's 2209, that means it was never unset. So it's kind of probably pointless to worry about that one much because they never did anything with it. What you'd be looking for is data that actually changes. So you can kind of look at that here. This is like the file comparator. It's just kind of a tool to look at and try to find out what seems important and what seems like it's changing.
So how many CAN buses are on the Tesla?
6.
At varying speeds, right?
Yeah, at various speeds. This program's kind of not done yet, so single multi-state doesn't work, range state doesn't work. Flow view is probably one of the things that's going to be, people are going to find the most interesting. This is actually a graphical way to do all of this. Here you can see the same type of bit field that I showed before. This is all the bits possible in the message. We have message 102 selected. When this comes up, everything that's black is a bit that is currently set in this message. Now, this has the same type of playback controls is the playback window where the green arrows are single step, stop, pause, play backwards, play forwards. So let's say if I'll slow this down because it's kind of hard to see otherwise. If I go at 205 playback speed and start playing this back, these are graphs of all of the data bytes. And you can see they're updating here for their current values. This allows you to see what the data bytes are doing on this ID as time goes on. The time axis is in seconds. So you can see how quickly all those bytes are changing as seconds go by.
Green is lit and red's off.
Yeah, green means that the current frame freshly set that bit, and red means that the current frame freshly unset that bit. That's as according to this reference, which the reference defaults to the very first frame in the capture. But what we can do here,
Can I change the reference?
you can change the reference to anything you want. Or you can set auto-reference here, which will automatically, every time I play a frame, right before we go to the next frame, it'll copy these values up here. So auto-reference will give you basically a delta of what bits changed from frame to frame. Now you're seeing just the bits that changed every time the frame updates. So that can be used kind of to see how the data changes over time. There's also another capability in here, trigger values. Let's say that you have a whole bunch of data and you only care when you get a certain data byte value. I'm going to play back through. I'll set that to 0xA2. Now I can speed this way up. Play it. And as soon as it hits A2 again, it stops. So you can use that to kind of step through the data, trying to find a pattern where that matches. If it's -1, it won't match anything. And you can just keep going. But that can kind of be used. I've used it when I knew that I wanted to find a certain area in the file, and it lets you zip through and find that area. So you can set this speed. You can go pretty quickly if you're just looking for patterns and you just kind of want to see what happens.
And you kind of have to relate this to the real world. If you get that speed going at about real time, then you have to think back, okay, I put my foot on the brake, then I moved it into drive, and then I backed up for about 4 or 5 seconds, and then I put it in drive instead of reverse, and went forward. And if you've got that in your mind, this makes kind of more sense. I'm looking for the point about where I put my foot on the brake or where I put it in reverse.
Have you ever thought about doing something like putting a GoPro camera in the back to watch everything you're doing? Like
Wouldn't that be great with a time mark on it, key
Yeah,
to
you'd have to
the
synchronize
SavvyCAN? Man, great minds think alike.
SavvyCAN time counter.
We ain't got that done yet.
Yeah. One thing that is done, let's say that you're looking at this data and you find something interesting. Let's say this spike seems interesting to you. You can click on that there, and it highlights in the main list that very piece of data you just clicked on.
Right on.
That's it.
Have you got this yet associated where I can go back and forth with a graph?
Yes.
I don't know how to do that yet, and it's my main feature request. But you'll have to see the graph first.
I'm going to take a quick step back to show the DBC files, just because before we get to graphing, it's really handy to have the DBC file loaded. I'm going to load up Tesla version 8 here. Go quick through the DBC editor. This is where you would set up. I have inverter here as one of the nodes. The inverter sends these messages. And I've just got them labeled inverter message 1, 2, 3, 4, 5, 6. But these are the IDs that the inverter sends. So I know that the inverter will send messages with ID 106. I'm clicking here to the signal editor and come up with the messages that the inverter sends in ID 106. Its motor RPM, torque filtered, torque raw, and throttle are found in here. Now this is where the DBC edit is nice. You can see that torque, or the throttle, is stored in bit 6 here, or byte 6 here. It's stored across the whole thing. The byte length is 8. It really kind of doesn't matter whether I select in little endian or big endian, because it's all in the same byte. But they also scaled the throttle by 3.92. That's actually a guess on my part, because the throttle goes from 0 to 255. And this factor turns 255 into a percentage, so it just goes 0 to 100%. I've commented here that it's scaled 0 to 100%. So the DBC, like you said, it's kind of a dictionary, and it's a converter. It turns values that otherwise would be complicated. Here's a 14-bit signed integer. And this kind of shows how a little endian works. We're starting here, going through here, coming back to here, and 14-bit ends there, so we're not using the 15 and 16, because that's just the way that Tesla works. The minimum value is negative 16,000. Max value is 16,000 for that on the RPM here. So the RPM is stored 1-to-1 scale. That's just one scale. And we use the DBC editor like that to set these up so we don't have to do it again. This shows another neat thing the DBCs can do. We have the gear selector is in 228. And the gear, down here we have a value table. When the gear changes, a gear value of 1 or 2 is neutral, 3 is reverse, and 4 is drive. That lets us turn those numeric values into text values. Personally, to me, if I see that the gear is reverse instead of 3, that's a lot easier to interpret. So I'll go back here. With the data loaded, probably, if I say interpret frames here, now all those, all that stuff that I had in the DBC file, now if I click that, you see that was inverter message 1. The motor RPMs at the time were 6162. The torque was only 0.6 Newton meters, and the throttle was at 15.288%. That is a lot easier than seeing 06, 80, 06, 00, 12, 18, 27. That's the power of a DBC file. This, for all intent and purpose, might as well be garbage according to people. I don't know what that means. Nobody really knows. I mean, you can't tell what that means very easily. Our goal is to build a DBC file so that you never have to think about that again. Anything that we've interpreted, I have steering position here. You see the position is, I think I have 0 as straight up and down, and it goes negative one direction and positive the other. But with the DBC file, you can see the various data without having to interpret it yourself. So that's kind of handy. Now on to the graphing window. You right-click on this, say Add New Graph. The power of a DBC file is I can select things from the DBC file that I want to graph. Let's say I want to graph motor RPMs, and it fills all this in for you. Ordinarily, the RPM is found in ID 0 or 106. It's found in bytes 5 and 4, with 5 being the high byte and 4 being the low byte. It is signed, and remember I said it was a 14-bit value, so the mask here masks off the top 2 bits so they don't interfere with us. The scale and bias are all pretty standard. The RPM is stored that way. And here we have the RPM graphed pretty cleanly. Now one thing you can do on this, let's say I want to zoom in here. We're looking at some data here. and I'd like to have the graph update while I'm looking at this so that the windows are synchronized, you can say synchronize windows here, click, and now the graph physically moves. So the graph is centered on the data that you're currently looking at.
Okay,
So that can kind of help to correlate. And once again, with the graph window, let's say I'm looking through here, and I wonder what's going on right here. If I double click that, that's selected on this window now. All the windows kind of synchronize that way, where if you click in one of the three windows, it'll automatically bring up the data in the other windows. So even the flow view here should have automatically updated to what I just clicked on in the graph. And then when I click here, the graph will also move automatically, showing me the current position of flow view. So that helps you to look at multiple windows at once and correlate what's going on. And add here another graph, motor torque, probably out there somewhere. Motor torque is unfortunately nowhere near the scale of RPM, but what we can do is select motor torque filtered here, edit the selected graph. Let's say I want, instead of that, we'll do a scale of 10. Now that's a little nicer. You can click on the axes here and scroll just one axis at a time, scale it, scroll it around, click this one, widen that out, and now you can see a graph of motor RPM versus torque. So he had a quick regen here, quite a bit of torque here. You can see that torque did cause the RPM to go up. Kind of resting here. The RPM stayed steady. Torqued again, the RPMs went up. Had a regen here, and it went down, followed by acceleration, and it went back up. So that's an easy way to graph data. You do not have to graph DBC files. Say that I knew that there was something that I wanted to graph. You can come in here manually and say I want to graph byte 3.
let's throw throttle on
So I'm going to take throttle and scale it up a bit because all these other graphs are pretty large.
Really?
Offset. I thought the throttle isn't stored right in the DBC file. Yeah, he was on the throttle an awful lot.
Like a Super Bowl clock full.
The right foot of a Formula One guy.
Oh, yeah, it's not set right.
byte 6.
It's just byte 6. There we are. So that's throttle.
We correlate the change in throttle to the change in RPM. Torque.
And all these too, you can see it automatically named these graphs based on what the DBC file said, but if I double click on it, you can name it anything you want. And also right clicking, you might see, you can save this graph image to file. It'll save the current view to a PDF. So you can use that. We do that back and forth in the developers list. Sometimes I'll show people what I'm seeing, how I'm interpreting the data. Sometimes I'm just being stupid and people will tell me that. But at least if you show other people the data, they can tell you, yes, that looks good, no, it doesn't look good. You can save graph definitions to file to save the way that you have this set up. Or I'll remove all these graphs in a minute and show you loading a graph definition. Throttle graph 7 there. I've scaled everything over top of each other. What we were doing here is trying to see, quite often the Tesla has quite a bit of data that is duplicated on the bus. Here we have 3 signals that I've pretty much worked right over top of each other. Or no, those 2 signals are almost over top of each other. This, I think, was miles per hour. And these are throttles and some mystery signal that we didn't know about.
And this is kind of tricky. You'll throw up a signal looking for a relationship to another signal, and you think it's somehow related. As you change the scale and offset, it gets closer to the one you're comparing it to. And I'm sitting there working for 30 minutes, and finally it dawns on me, this is exactly the same signal.
And you can see on this,
And
they
then
aren't
torque is the one
exactly
that
the
comes
same
to mind.
signal.
It shows up
But we didn't know
different
why.
places.
So that kind of lets you keep a reference of, here's cruise investigation. I have a lot of signals. I'm trying to correlate back together. I think this was the actual cruise signal.
Random feature request, could you add integration and derivatives to signals? Because in theory, if you were to integrate your torque, that would give you your RPMs, and that would at least help you correlate different types of signals.
Yeah, we probably
Not
could
really.
do that.
It wouldn't really.
Not necessarily perfectly.
No, not even close. I mean, that would assume there's no losses in the system, which of course there are.
How much weight it carries.
You're making assumptions, but there are certain types of signals that are related to each other. They're sensing different things.
There is. The problem is we get too much of that. And that's what I was saying about blowing it up and matching them in the scale. The offset and the scale will be different in 2 different messages. And so, but I'm trying to get them to appear on the screen as the same. When you blow it up to a certain level, you're only looking at the noise. If the noise is the same between the 2, you're looking at the same signal. And so I constantly thought I had a find, and I found another version at torque somewhere.
Yeah, it's actually, I wonder if I have it stored on here. I think it was actually, I'm booted into Windows right now. I think I did it on Linux. But there was, in our cruise control investigation, I found like 8 torque values that I have all lined up over top of each other. So that's another difficulty sometimes in reverse engineering. You'll find the same data in 14 places, and you don't know which ones are copies and which one's the master that actually controls anything.
Right. What's the message to and what's the message from? Where's it actually originated? And what I'm talking about is you don't know. These could be related, but you blow this up and up and up until this noise is a waveform. If that matches, you're looking at the same signal. It's not related, it's the same thing. Because the
Kind of
noise
see
will
that,
vary from what.
like these 2 signals, what he's talking about, even their noise almost matches. One of them is a little bit blockier than the other, has starker transitions, but even the noise on those 2 signals pretty much agrees. So you have to believe that that's the same signal, just sent by 2 different things. I don't quite have the scale right on this one, but it certainly appears to us to be the exact same signal. It responds the same way. So we're seeing these 2 signals, and then we wonder which is the master and which is just replaying data. It appears that what happens is a master will be sent, and then you'll get a slave, say, that sends to the dash cluster for your miles per hour, and then a slave that gets sent to your traction control for the miles per hour. And so you don't know which one is the slave data and which one's the master that actually controls RPMs.
There's no time phase shift in those signals?
Sometimes you can see it. You can kind of go in here and try. Like with this, if I really zoom in, that's kind of the usefulness of being able to zoom in one axis. It looks kind of like the red one is responding first. But not by a lot. And because it's blockier, sometimes it's still kind of hard to tell really who's following who. But zoomed way in, you can look. It would be my theory that the red one is the master because it seems to respond just a fraction before the other copy.
If you were to look at the two individual CAN messages, if you were to see a large change.
You could, yeah, we could.
You might be able to use that.
You know, you can click like that and come in here. That's 106, and the other signal is 102. So you could try to look in here. 102 is sent first. You might theorize then that because it's sent 5 milliseconds before, that it's the actual master and this one copied the data. But it's still a guess. We kind of have to sometimes guess, and we'll say 102 is probably that value, and try it and see if it responds. But there is a lot of trial and error in reverse engineering.
Did you have any clue going in which bus contained which
We did.
signals?
We were able to cheat on that one because he has the Tesla schematics, and they do actually tell you which buses are what. The powertrain bus we knew was bus 3, so we knew which one to go on. So at least we had a head start there in that we didn't have to look at 6 CAN buses not knowing any idea of which one the data would be found on.
It's a chicken and egg question, but would this software suite, as you've got it, would it have speeded up the cracking of the UQM?
No, not really.
Okay.
What I did for, I don't know if there's an easy way for me to show it in here. Gear on the Tesla does have a security byte. This final byte here is the security byte, 7F. What I did, I had to crack that too. What I did is I'll filter to only 228 so we can kind of show how that process works real quick. So you have all these messages from the ECU of, it's only 4 bytes. Most of them stay the same. This byte here where it says C0 is actually the gear selector. It goes, I believe, C2, C4, D0. When that changes, when anything changes here, the security byte changes. You can see this is kind of a counter on the last byte. The upper 4 bits here are counting as you go down. So every time it counts, you have a different security byte. If this changed for gear, the security byte would change too. So what I could see is that the security byte was based on these 3 bytes here. And this program doesn't help me to crack that, but in a nutshell, what I would do is try to find a baseline, like say 0, 0, or a baseline 0 here where the counter is 0 and these are set as B2. I would look for 1 bit difference in the messages, which this is 1 bit different than this. Changed it to 7F instead of B2. What I would do then is take exclusive OR of these 2 values and find out what happened when 1 bit changed in the message. And that would give me a value. Then I'd try for a different one. This is 1 bit different than this. So then I could do an exclusive OR between these 2 and find that difference. This is the 2 bits that changed here together. So I would double check this by taking B2, XOR the 2 values I got here, and it would come out to F8. Kind of difficult to explain, but that's how you find out bit field differences and crack those codes.
And let me jump in and disagree with everything you said. Collin is kind of focused on the security byte in the UQM. There was a whole lot of work going on in an Excel spreadsheet to find out the bit patterns for forward and reverse and neutral and that sort of thing, that this would have made tons easier.
Mm-hmm. Yeah, but his
Or-
question
or
was
the rest
specifically
of-
whether cracking the security byte would.
No, it said reverse engineering the UQM.
Oh, yeah.
control.
I guess to some
Yeah, the broader
extent,
question.
yeah.
You jumped right to the security byte.
I thought he meant the security byte.
Well,
But
that
yeah,
was the key to getting the thing to work, was the
But
security.
yeah,
byte.
the rest
We
of
didn't
it
know
would
how to
have
put
been
it
far
in
easier
forward or reverse.
with
That's
this
what- They
software.
have all the answers.
Yeah.
There's some things that the software doesn't really help with. The reverse engineering the security byte kind of is a manual process that I end up doing. But the rest of it, like I said, the gear is found here. So what we could do with this program is looking here and see when there were differences. That's actually a good point. I can go in here to, say, frame data analysis. I know now that 228 is the gear selector, and I know that byte 1 is the selector. He actually never changed gears this whole time, so we can kind of go in here.
So it would have made the UQM publishes their CAN data if you buy the motor.
From them, yeah.
Right.
Yeah, things
Except
like that
we
would
can
have been a
run
lot
Coda,
easier with the
And it didn't
UQM.
use the UQM scheme. They had a whole different software thing.
They had their proprietary DCM.
Right.
Yeah,
And so we had to reverse engineer the whole control of the UQM inverter. And one of the problems was in the message that carried the real torque command, it had this byte at the end of it, a CRC byte of some sort that was
The bite me bite.
the bite me byte. Collin cracked it.
Yeah, so
That,
this,
that level of it, this can't do. He had to manually work out how to do that. But for the rest of what we had to decode, this would have been.
Yeah.
it would
This
have cut
shows
the
here.
time into a tenth.
see, this is the byte that I said stores the gear. So if you were using this program, you can see most of the time the gear was not set. But when it did, you can see these set values. That tells us what values we would need to set to change gears. And you can kind of help define this by, if you don't know where the gear is, but you want to find out, what you do is shift it in park, drive, park, drive, park, drive, park, drive. And you're looking for patterns that change like that. And you can see that he had it between 3 different gear selectors there. So the program is useful there to help find mystery data. If we had this for the UQM, we could have more easily verified
And
what
the
bytes
UQM
did
was
what.
fairly simple. When you go into reverse, a bit is set and left there. And when you take it out of reverse and go into drive, that one goes dark and another one comes up. Mark Weisheimer actually worked that out. But in the case of the Tesla, bizarrely, you change this value and you have to send about 9 frames minimum, 9 to 18 frames. And then you go back to normal operation, and the inverter picks this up and recognizes it as valid because of that clock and the security byte at the end. So it only flashes up there for 8 or 9 frames, and this is, I think, 100 millisecond, or maybe it was a 20 millisecond frame rate. And then it goes away.
Yeah,
So you
this-
don't have a state machine, it's just a signal that the inverter has to catch.
There's the graph of setting gears on a Tesla. This is what caused us to have a little bit of trouble in finding the gears. Here's setting a gear.
That whole thing flies by in 100 milliseconds.
Oh, yeah.
Here's setting a gear. That's it. The rest of the time, nothing happened.
So do you use that procedure of quickly toggling through park, neutral, drive, and wherever, obviously this will...
Yeah, what you would see is when you park, when you're toggling, you would see these blips appear. And so you could actually...
But in that bite, what was confusing was just going down the road in drive, it's exactly the same value as going down the road in reverse.
Yeah.
Or being parked.
The gear just plain disappears as soon as it's set. It's set. This is only about 3 or 4 frames probably.
So you just changed the state machine and the inverter only went back to normal.
Yeah.
Right.
It's like an enabling state
It's
change.
just an enable state change. The inverter, once, there's probably some form of feedback loop that we don't know about where the inverter tells the ECU that it's gotten the gear. Because there's a variable number
Yes.
of frames. Sometimes it sends 5 frames, sometimes it sends 2 frames, sometimes it sends 7. So it seems like the inverter takes a while to pick it up and issue a reply that we don't know about.
So we have a 16-bit clock. If I want to change the gears, I just use the whole clock. We send 16 frames, and that always seems to be enough.
Good to go.
Yeah.
Because I don't know what the feedback is I've got to change. But 16.
We don't have the rest of the cars, so
And that's
that's not needed.
Right.
Yeah, that's a good thing to keep in mind with reverse engineering too. You only have to reverse engineer so much. There's probably 95% of the traffic on the Tesla bus, we don't know what it does. It's irrelevant.
We won't be using it.
Once you get the important stuff, the gear and how to, on an inverter, once you can make it drive down the road, that's the important part. So, if you were hacking a car and you were trying to do something malicious, once you do the malicious thing, you don't care about anything else in the car. It's just,
Sit back and watch the flames.
you just try to find out the one thing you're interested in and try not to think too hard about all the things you don't know. Any other questions?
Yeah, I've got 6 temperatures out of the inverter. I don't need 6 temperatures.
No.
Which one's the inverter and which one's the motor? And I'm kind of guessing, but it's a pretty good guess.
6 temperatures, 6
gas
IPs.
Which one changes temperature faster? It's probably the inverter.
That those may be setting some diagnostic codes we don't know about.
What am I going to do with the other 4 temperatures?
Without the
I'm not ever
Tesla
gonna do
ECU,
anything.
nothing.
And that's probably, you come into like integration. Different components have different IDs, then they get stuff. That's why they repeat stuff.
Yeah, it like I said, it seems like you'll get messages that are specifically targeted to certain devices on the network. You'll have one device wants, or several devices might want something like miles per hour, so they know how fast the car is going. But they literally don't all listen to the same message. They're all looking at different messages that just happen to have the same data 8 times.
Well, from a design standpoint, if I could build a thing that only listens to one message, it's easier to code.
Yeah, that is the key. Jack had covered filtering yesterday. Most devices on the CAN bus aren't like SavvyCAN where they're listening to the whole bus. This program I specifically designed, we torture tested the thing up to like 7,000 or 8,000 frames per second. And little things on the bus, they probably aren't coded to handle 8,000 incoming messages a second. They'd be overloaded and they wouldn't work at all. So they normally filter and only accept the messages they really care about. So you're going to get devices on the network that have a filter for 3 messages, let's say. That's the only messages they listen to, the only messages that come into that. So that's probably why the duplication is there. They're all listening for different messages and filtering out everything they don't care about.
When we get on and listen to everything, the data rate gets pretty high.
Yeah, the drive bus is about 1,800 frames per second. So it's more than 1 frame every millisecond.